I'm going to talk about, essentially, I'm going to talk about symmetries. Well, the talk I'm giving today is a kind of overview of the very recent preprint that I just posted. So it's a rather long work, so on 60 pages. So I'm giving the general idea of what was done. So the idea is to the whole idea is about the symmetry group of the Euler system, which is, as we know, it's valid in the inertial interval over the developed turbulence. So not the full symmetry group, but just the special part of it, which is most usually mentioned, which is a sum of the Galilean group. So Galilean group is temporal translation, spatial translation, rotation, Galilean transformation, and spatial temporal scaling group, which means scaling of time and scaling of space. So these are all transformations which keep Euler system invariant. And in fact, all these components will be important for us except for rotation. I just kept rotation because it's part of the Galilean group. So the idea that we will follow is we will not use equations at all. So we only use this group, the bigger group, so the sum of the two groups. And what I will try to convince you is that there is more in this group than the group itself. So essentially, the result is that there are extra symmetries which are generated by just solely by this group, which are symmetries on the statistical level, and they are not an element of this group itself. So there are extra symmetries which we will call hidden symmetries. So this looks a bit counterintuitive, but we'll see that it is so. So I will start with a general framework. So how we will study the system. So I said that equation of motion, I don't care. I just care about the system. So the mathematical formulation is that we have some configurational space of configurations, which we call capital X, and small x is its elements. So for the equation x, small x would be the full velocity field at a given time. And we will consider the dynamics in a probabilistic sense. So we assume that this space X is equipped with some there is a probability measure space and there is probability measure mu. So the way we will describe the dynamics is just simply dynamical system way. So we assume that there is a flow evolution operator. So in dynamic system, evolution operator is called flow. So it's not flow of the liquid, but it's a flow in a dynamical system way. So we will call it flow, which simply, given the state at time 0, phi t gives the state at time t. No? So this is time translation. And as I said, we'll be talking about the statistical description. So statistical description of the what we know as a stationary statistical state is a probability measure which is invariant with respect to the flow.
Excuse me, this is an Eulerian coordinates indeed.
Okay, yeah. You may think it's Eulerian coordinates, yes. So far, yeah. So this expression exactly means that the measure in the invariant and the first. So you see this is flow. And this is musical symbol sharp. It denotes that it is an image of the measure by the flow. So push forward of the measure by the flow. So where the measure is pushed to different time, it doesn't change. So this is invariance. And then in addition to the flow, the symmetries that I just mentioned in the previous slide, they give operators. So they give operators or maps in the space X, which you can think as a symmetry transformation considered at given time, or like at time 0. So there is a special translation, so you just change coordinates. There is a rotation. There is Galilean transformation, which is just subtracting the constant speed. there is a temporal scaling, and there is a spatial scaling. So there is a set of these symmetry operators, and we will be interested on the action of these operators on measures. So essentially, what we say when I say that these maps are symmetries, I just mean that the map maps space to itself, and whenever it is applied to an invariant measure, it gives an invariant measure. So it does not break invariance of the measure. So this is symmetry. So it's a big weaker definition of the symmetry. So it just means that this transformation does not break invariance of the statistics. And all of these operators are symmetries, actually, except of Galilean transformation, which is also symmetry under some extra condition. So, and also the vocabulary is, we say that measure is, so we know that whenever you take invariant measure, applying the symmetry, it gives us another invariant measure. So if there is the same, we just say that measure is symmetric with respect to this S. So this is a setting. So we will work in this setting. Yep. So now, having these maps in explicit way, so this is flow, special scaling, special rotations, Galilean transformation, temporal scaling, and special scaling. So there is this set of maps. We can write all commutation relations. So how you understand it is as phi t composed with SR equal SR composed with phi t. So it means that they commute. So there is all kind of relations. So it's a kind of commutation relation. So most of them commute, but some of them don't. And this will be the crucial point. So the two commutation relations that will actually are in the basis of the whole work is there are two symmetries that do not commute with the flow, with evolution. The first is a temporal scaling. So if you first change time by the factor of a, and then consider evolution in time t, it's the same as first considering evolution with in time t divided by a, and then changing time. So you see that it's not, they do not commute exactly because the argument of the flow operator is different. So here's t divided by a. So it's a almost commute but do not. And another relation is a Galilean transformation. So it tells that if you first make a Galilean transformation and then evolve, it's the same as you first evolve, then you make Galilean transformation, but then you have to shift because the two systems will be in different positions. So we shift and then it becomes an identity. So essentially these two commutation relations will be central. Just I have to drink. Will be central to our study, and actually, this table that you see in this page is a formulation of the problem. So I will not use at all any equation of motion. I will only use them as an application of the results, but the whole all results are just about the table, and the table is a definition. So actually, we by putting this table as a definition, we overcome many complicated questions, for example, of existence of the flow or semi-flow operator for Navier-Stokes, for Euler, etc. So here we just assume that it exists, and we assume that it have commutation relations with all other. This commutation relation with all the symmetries, which is I think
a provocative question. Isn't this kind of abstract things a little bit like considering categories?
Well, it's in the sense that it's maybe there will be some spirit, because as you will see, I will have a strongly algebraic approach to consider them, just from starting from the next slide. So from that point of view, yes, I would not say, I'm not sure about categories, but the fact that it will be algebraic approach, purely algebraic approach, yes.
Thank you.
So now let's go. And so what I want to say is that because of these two relations, because of this fact that there are symmetries which do not commute with the flow, I will show that you can construct different symmetries. So symmetries which are not in a list. Yeah, so that's a point. And these symmetries may be important for turbulence. Okay, so so we have two non-commuting symmetries, and the first part where I will try to give more details is about temporal scaling. So let's forget about Galilean transformation completely, and so let's consider just this second temporal scaling relation. So this is the first part. So the first part will be simpler. So we will consider smaller group just to make it it's kind of warm up, and also it applies nicely to the some kind of models. So we consider just the symmetry. We consider two parts of the symmetry. So first, which I call this HTS, it's temporal scaling. So the first temporal scaling, well, this is a little abuse. So it's HA. HA is a temporal scaling, which means that you just divide velocity field by A. So this is one symmetry, and another symmetry we will call G is special scaling. So let's consider temporal scaling as H, and G is a special scaling, or can be also rotation. So what is important is that H, G, and flow will satisfy this set of four commutation relations. So first relation tells that if you change scale time with factor A1, then you scale time vice versa. First scale time with factor A2, then A1 is the same as scaling time with respect to the product. So this is clear. So this is this form of the temporal scaling. Then the next is that we assume that this group G, this element G, commute with the flow. And indeed, like special scaling rotations commute with the flow. Then G commutes with H, which means that like special scaling commutes with temporal scaling. This is okay. So important, the relation is the last one, which I already mentioned, is that the flow does not commute with temporal scaling. So if you first change time and then evolve, it's not the same as first evolve and then change time. It's the same as you evolve with in a different time and then make a scaling. So so now what I want to do, I have two types of group of elements, and I want to remove the first somehow. I will make a kind of projection with respect to the first, and in a way which will preserve the second. So how we do it, we infer this algebraic notion of equivalence relation. So we say that our system state, two system states are equivalent if one can be obtained from another by the temporal scaling. So if x prime can be obtained just by changing scaling time of x, we say that just they're equivalent, so they belong to the same equivalence class. So Ex is a set of all states which just obtained by scaling time. So in a space of configuration space, so each equivalence class is a straight line, yeah, because you have this one parameter scaling group, and we will now try to consider dynamics on a space of these equivalence classes. Yeah? So we will not. We will disconsider the difference between the states if they just obtained from one from another by changing time, by changing scaling time. So this would be very nice if and this would work directly if we didn't have this problem about non-commutation. So the problem about non-commuting the fact is that if you take two different states from the same equivalence class and evolve them with respect to the same time, they do not belong anymore to the same equivalence class. So we cannot directly have a dynamics on equivalence classes. So just for those who are more familiar with algebra, so this foliation of the space to the equivalence classes is also carries the name of quotient space. Okay, so what we do? So what we do is we notify that actually they do not commute, okay, but they almost commute. So they almost commute in the sense that the time is different. So it's t divided by a. So what happens is that if you have a state x, which you translate it at time t, and then you have another state x prime, which is on the same equivalence class, and you want it translated in such a way that it belongs to the same equivalence class as this phi t x. So we just need to translate it to time t prime. So we just need to synchronize the watch of x prime with the watch of the x. So we have to translate it to different time. So what it does mean is that it means that in fact you can think of evolution of dynamical system on equivalence classes if you properly synchronize the watches on every trajectory. So you need to synchronize the watch on every trajectory, and synchronize means that you need to always have some reference element with respect to which you synchronize your watch. So this comes to this definition. So what we say is that we define a representative set. Representative set is just a set, one codimension one set, which contains one element in each equivalence class. So for each equivalence class, we choose one element. We call it y. And globally, we can define the set y capital, which contains one element in each equivalence class. So we say that y is a representative set if it contains one element in each equivalence class. And this gives us the function a, which is defines the projection. So the function a gives the following. So whenever you have any state x, the function a tells you how much you should rescale your time in order to be projected to the representative set. So we get a concept of projection. Okay, so this is the setting. So and it turned out that actually with this definition we can define the flow and measure and all kind of structure just now restricted to this representative set. So we can actually project the full dynamics and full statistics just on the representative set. But it's a non-trivial projection because we need to change time in a somewhat complicated way. So how we do that? This central kind of lemma that I use from ergodic theory, it tells you that whenever you have any function a of x which is measurable, so the function which tells you how to project on the representative set, you immediately define a new flow, which is which has now the time which is rescaled with this rate. And also, if you have an invariant measure for the original systems, that new flow has also new invariant measure, which is just obtained for some relations, the explicit relation. So essentially, the main theorem, there are two main important theorems which are proved. Is the first is that whenever you have this structure and whenever you have a flow on a full space, an invariant measure of the full space, you can define a flow on a representative space on this pink codimension one set, and it will be obtained as a composition of this measure this flow which obtained through the change of time by this ergodic theory result, and projected. So you change time and project. So you have to change time and project, and you have to change time in. So it's not anymore. You see that change of time is not anymore linear. It's a it's a non-linear trajectory dependent change of time. So you change time and project. So you get a new flow. It's a flow, and moreover, this new flow has a invariant probability measure, which is obtained from original measure by changing time and projecting. So this kind of projection and changing time gives us completely dynamics on this representative set. So on some set smaller. So so before the next picture, we should understand that since we projected kind of, we removed one dimension from our system, so it's actually not so much because the usual system is infinite dimensional, but we removed one dimension. So now we can have symmetries which were not present in original system, right? Because it's a system which has slightly less information than the original. So this is the second theorem. So the second theorem tells you that whatever group element G that satisfies commutation relation that I showed there, it becomes a statistical symmetry for the new flow on a representative set. So it becomes a statistical symmetry in the sense it's not anymore a map, but it gives you the rule how you can transform a measure, invariant measure, so that you get a new scaled invariant measure. So it's already a more complex relation. So you first change time in some way, and then you project it in some way. So there is a formula. Very important that there is a formula which transforms what any invariant measure for this reduced normalized. So we will call this normalized. No, so the flow on the flow and measure on the representative set will be called normalized. So on the normalized flow, we keep the same group, the same symmetry group G, and just it's a group which acts on the measures, and it gives new invariant measures. So this is it. And this gives us the concept of hidden scaling symmetry. So what you can prove is that if the measure of original system had a single symmetry, whatever kind of symmetry of this kind or whatever combination, automatically the normalized measure will have this normalized symmetry, okay? But not vice versa. So in normalized system, measure can be symmetric, but at the same time, all measures of the original system broken. So despite so it tells you that all symmetries of the original Galilean or special temporal scaling symmetries can be broken, but still you can have symmetry on the for the normalized system, which is still unbroken. So this is the main message. Okay, and now we will just show how it works. So up to now it was very algebraic. So I apologize. So it was probably it's probably more clear for mathematicians. So but now I will show how it directly works for the system. So since we constructed this symmetry with just with a group, so it applies to any system which has this group, and we will consider shell model of turbulence. So well, I think many here are familiar. So shell model of turbulence means that you have shells, which is shell 0, 1, 2, 3, 4, and so on, and integer numbers. To each shell you associate wave number, which is 2 power n, so 2, 4, 8, and so on. And then at each shell, each scale or each wave number is described by the complex time-dependent variables, which mimics fluctuations at this scale. And they satisfy equation which is looks like Navier-Stokes. And if you remove viscosity, if you remove forcing, you get analog of the Euler equation, and you directly have these symmetries. You have the temporal scaling and you have spatial scaling. So there are two symmetries. One is H for our, which one was HA in our previous slides, another was J. So HA is a temporal scaling and J is a spatial scaling, which is discrete for the shell model. So now, now we just apply directly this normalization that was suggested on a group level. So what you need to do is you need to define this function AX, which was defining before, if you remember, the representative set. So AX is just a function which defines a characteristic time scale for the state X. Okay, so it's actually turnover time, turnover frequency, better say. So I didn't show you the theorem. So all symmetry properties do not depend on the choice of AX. So you can choose whatever good function that you want. So we will be choosing this function, which is a kind of filtered entropy. So what we do, the new variables, normalized variables, is just defining un by this a, and new time is just integrating this a along the trajectory. So what we do is at every time moment of time, we renormalize our state and our time with respect to with respect to turnover time, which we measure at that moment. So this is what we do. So we have explicit expression for the new variables for the new time. You can explicitly write equations of motion. And we have this special symmetry for normalized symmetry with G star. And what this symmetry means is it means that you can, that this new equation has a rather complicated change of variables and time. So you can change variables with this denominator, which is given by this formula. And also you change time, which do not change equations. So you can just directly check that this nonlinear transformation of state and time just do not change equations at all. Okay. And we can check it. First of all, this picture is just maybe to understand what does it mean going to normalization. Normalization means that, so this is the evolution of in time of some shell variable deep in the inertial range. So, and what you see is that nothing happens. So this is kind of laminar flow, then poof, small burst, then small burst, and nothing happens, and then strong burst. So this is intermittency, right, that we used to see. So what you do by normalization, you rescale your state in the vertical direction, and you stretch or compress time in a horizontal direction such that it always fits to the turnover time at the same moment. So so after this normalization, this intermittent behavior becomes this curve which you see below, which is kind of nice looking. No, it's never too large, never too slow, and never too fast, and so on. So it kind of put it to the variables where everything goes nicely. And actually, we can just directly check. So now we have a system with new variables, new variable shell variables, new time variables, and they have a new symmetry. So we can just check that the statistics of our shell model is invariant with respect to the symmetry, and we can just check. This is checked on this picture. So there is this symmetry which we apply with different m, and it's applied with m from 12 to 21, and for different shells we see that full collapse of the curve. So it is very. So we can see numerically that this symmetry is very nicely supported by numerical simulations. So the last message of this slide is kind of coming to the ground of what maybe people are more familiar is the Kolmogorov multipliers. So we know that it's known that Kolmogorov multipliers have invariant statistics. So this comes from, goes back to the Kolmogorov 1962 work. And multipliers for shell model is just ratio of the two adjacent shells. And it was shown in these works in 93 and 2003 that these multipliers have very nice universal statistics, which means it doesn't depend on m. So in terms of the normalized variables, multipliers can be written in terms of normalized variables from the construction I just see. So in that sense, the hidden scaling, hidden symmetry immediately gives, as a consequence, universality of multipliers. So this is a hidden symmetry. He's proposed as theoretical explanation why multipliers are universal. So it's just byproduct of this symmetry. Okay. So on the next page is what the symmetry is for. And here I will go really briefly. So I have a question. So I started somewhere.
You started at 40. You started at 40.
And when I should finish? So it's
45 minutes, and then there's going to be
45 minutes. No? Okay, so I still have.
No, 40. You have 45 minutes.
Okay.
For you to...
Well, I have 50 minutes more. No?
Yes.
Oh,
14.
20.
Yes.
Okay, so it's perfect. So so the main application of this symmetry is a structure function. So the first part of the slide is to show that structure functions they actually not they don't need Navier-Stokes equation or Euler equation in order to be defined. We can define them purely in terms of the group symmetry. So we can forget about equation and just define it from a group. So how to do it? So first, let us remember what this structure function means. So the structure function for usual turbulence is that you consider the distance, so fixed distance L, and then you consider the change of velocity fluctuation is this distance, and then you take a norm of it or projection, whatever, take power P, and P is order of the structure function, and average in any way. So this gives you a structure functions, and we know that this structure function has this special parallel scaling, intermittency, and anomaly, and so on and so forth. So what I can substitute this definition by the definition which is written below. So what is written is that I take whatever function f, I combine it with a special scaling, with a factor b, with a coefficient b. I need some prefactor just to make it dimension correct. And then I say that this is a structure functions order p if function f has satisfies the following scaling relation. So f combined with temporal scaling is f divided by a power p. So this is just definition, but what is important is this definition is purely in terms of symmetries. So I don't have any flow, any velocity fields, nothing here. So it's just in terms of symmetries. And this definition includes our original, the original definition from the first line. You just take the function fx in this form, and then you come back to the first line. Yeah? But this definition is more general, and with this definition we can work algebraically, just directly applying the whole result that I had before. So I will not, I cannot go into any details here, but I will just announce what is done. So first, you can show that if your measure, the normalized measure, has a hidden scaling symmetry, so it has this G star symmetry, so it's symmetric with respect to G star, so it's exactly what we checked here. So for the shell model, if this normalized symmetry applied to normalized measure does not change it, then this function will have a power law scaling, which will depend only on P. No? So whatever function for f you put here. And the scaling exponents you can compute, well, not compute, you can define them as Perron-Frobenius as eigenvalues of some positive linear operators. So you can define.
I suppose you have some constraints of positive indefiniteness, etc.
Sure. Yes, sure. You're right. Yeah, you're right. Yeah, there are some constraints. So there are positive definite. There are some non-degeneracy constraints. Some integrals should not be zero, should not be infinity. So, so I'm giving very superficial. You know? So you can define linear operator, which is directly comes from the symmetry of the normalized measure, and then zeta p will be obtained through Perron-Frobenius eigenvalue. Also, it can be directly seen that there is no restriction that there is no conflict with intermittency. So the zeta p, which are given by this Perron-Frobenius eigenvalues, they typically intermittent, so they're typically non-linear in P. And now I'll just show how this works for the shell models. I'll skip this slide. So for shell model, it numerics. somehow you have to work with the operator which is in infinite dimensional space, so you cannot make it treat it numerically. And it's actually quite heavy numerical work, heavy for the computer. But you can approximate this operator. You make approximation of this operator. So like first order approximation, second order, third order approximation, like you Taylor approximation, let's say. So
are you not losing the structures of these groups, etc., by these approximations?
Well, I would not say essentially what this approximation does if go into the details. So the main part of this operator is a conditional probability of the multiplier at given shell with respect to the multipliers at the previous shells, let's say. So what approximation does, it's a first approximation, you say that we only condition to the previous one. The second order approximation is we condition with respect to previous two, and then with the previous three, and so on. So if there is locality, if there will be convergence, then everything should converge. So group, we don't lose group, but we lose correlations. Yeah, and these are numerics which show how it was done. So this green was the first order approximation, blue second order approximation, black is third order approximation. The red is numerical exact data. So this is for Sabra model. These green points are Kolmogorov. So what you can see is for the first order structure function, you have a very almost perfect match. So this is Kolmogorov, and this is all of them fall exactly to this, more or less 0.4. For the second structure function, 2. So this is first order approximation, second, third. So it goes in the right direction. Almost arrived, but still did not converge satisfactory, but already passed the Kolmogorov value. And for higher order, it's already slightly worse, but it's converging. So I would say the results are very nice for low order moments. It's not contradictory, but also not satisfactory for high order moments. But at the same time, I would say that it's not surprising that high order moments do not converge, because we know that the shell model, the intermittency of the shell model is related to the long correlated structures. So, and higher the moment you want to check, the stronger is the correlation between the different shells. So it's a natural that convergence is getting worse at larger order moments. So we have this. So now I'm coming to the very last part. How to apply it to the real turbulence. So real turbulence, and this is a standard critics, is that Y-shell model is not real turbulence because there is sweeping effect. Yeah? So let's consider how to remove sweeping effect. So in order to remove sweeping effect, surprisingly, what we have to do in our construction is to consider the second non-commutation relation. So we already considered the first relation, which is telling that the flow does not commute with the temporal scaling. And now we have just one more symmetry which does not commute with the flow, which is Galilean transformation. So now we will do exactly the same construction, but with respect to the both these symmetries. So what we do is we consider the group, which is just a sum of the temporal scaling Galilean transformation. So all elements is you change time and you rescale time, and you go to another reference frame. And now we define equivalence relation with respect to this symmetry group. So now two states are equivalent if one can be obtained from another by scaling time and going to another Galilean frame. Again, we have this problem of the equivalence is not flow invariant, so we have to repair invariance with respect to the flow, and it still can be done, but now it can be because of the form of this commutation relation in order to repair it. So you see, if you if you consider the state x which goes to this position, if you want to state x prime also to go to the same equivalence class, you have to do two things. First, you should evolve to time t prime as we did before, so a different time. But then we also have to shift to the time dependent value. So by the change of time and shift, you can repair equivalence. And this is, so repairing this equivalence means that you can synchronize all these dynamics with respect to the representative set. So now representative set is defined in a similar way. It's a representative set which gives you one representative element for each equivalence class. And we can do the same thing. So we can define normalized system, a normalized measure on this representative set. So there is a flow, there is a normalized measure. So everything can be done in fairly similar way, though technically it's more difficult. And even more, we can keep group. Again, so what was important is the group of rotation special scaling still can be defined with this G star operation. So we have the hidden symmetry. So we can normalize and find the hidden symmetry, which is not element of the original group. Okay, so and here just small note is actually this construction is much more complicated, but well, more complicated, and it cannot be done as general as it was before, because in general simply doesn't work. You need extra conditions, and it's very curious what are the extra conditions. The extra conditions are actually special homogeneity of the measure. So we need homogeneity in space of the measure, which can be written in terms of algebra. And another condition is incompressibility. So it's actually a condition why it's called incompressibility. So it's a condition which comes from algebraic structure, but whenever you consider the representation of the group with the Euler equation, it's exactly incompressibility condition. So somehow this algebraic construction gives you another source of the importance of the incompressibility, because we know that incompressibility is important physically, so it gives different properties of the flow. We know that incompressibility is important from point of view of partial differential equations, because it makes the system non-local. But it turns out that incompressibility also naturally comes from this quotient construction. When you want to remove the Galilean transformation, somehow it only works if the system is incompressible, and it doesn't work if it's compressible. And this is I think this last, this is a last slide before the conclusion, is how this construction is applied to the real turbulence. So the Euler equation. So I'm just giving a final result. So when you apply this to the so what is the renormalized field that we obtain? So it's obtained, it's constructed in two steps. So first, you go from Eulerian transformation to the quasi-Lagrangian. So you subtract. So you see, you take the specific Lagrangian trajectory, RT, and then you go to the reference frame which moves with this Lagrangian particle. So you obtain quasi-Lagrangian representation just naturally from algebra. And then with this flow, and already since we go to quasi-Lagrangian representation, we don't have any more sweeping effect. So we removed sweeping effect. So there is no problem with this. And with this flow, we now renormalize. So we normalize with respect to with respect to turnover time at the same moment. We normalize both velocity field and time. So we go to the new time. In some sense, it's every solution goes with its own watch. And now you have this new function. It satisfies new equations, and this new equation has now the symmetry, which is hidden symmetry. So it's a symmetry, non-linear symmetry, where you have to change velocity field, you have to change time, and in a non-linear way, and it does not change equation. So it's a symmetry which is not in a group originally, but it appeared in a group just because we projected. And again, we have the same connection with Kolmogorov multipliers. So these are exactly very closely to Kolmogorov multipliers, considered Kolmogorov, a little bit generalized by in this work by Chen Aing Srinivasan, and they also checked both numerically and experimentally that these Kolmogorov multipliers are universal. So what it is a Kolmogorov multiplier is a ratio of velocity fluctuations at two different scales, and universality means that this ratio is universal in the sense that it does not depend on scale; it only depends on the ratio of the scales. And you can directly derive this universality from the hidden symmetry, from the universality of the normalized fields. Okay, so that's actually I finished. So what is the main message? The main message is that just having the original group, which is the sum of the Galilean group and special temporal scaling of time and space, we have two symmetries which do not commute with the flow, is temporal scaling and Galilean transformation. So we can remove these two symmetries by projection. So it's essentially a construction in the spirit of the quotient construction of factor group, or in the sense, so you factor it out, but factorization you factor it out in a somewhat is more complicated way, because you need to tune the system to, so it's not direct, no, because of this because they don't commute. And then you get a new system which has a hidden symmetry. So it's a symmetry which was not in the original system. And this system, and if your statistics, it's statistical symmetry. So if your statistics possess this symmetry, you automatically has power law asymptotic for structure functions. They are usually anomalous. And you have a framework how to compute these scaling exponents, because they can be computed as Perron-Frobenius eigenvalues of some special operators. And this, in principle, applies to any system which has this this group. So it can be quite general in this sense. So it's not at all linked to equation of motion. It's just linked to the group. I think I finished. Thank you.
Thank you, Alexei. Thanks so much. First question is by Kostya Khanin.
Alexei, nice talk. Thank you. I have to run very soon. I have another meeting coming, unfortunately. So I wanted to ask. So you started with a general scheme of dynamics on infinite dimensional space. You probably can also consider a situation where you take account of the spontaneous stochastization, or say that instead of dynamics, you have kind of Markov process. And then you consider, instead of invariant measure, stationary distributions of this Markov process.
I would say so, because
more realistic for Euler setting, I guess.
Yeah, yeah, it's very correct, very good remark, because we don't know in which sense there is a flow in Euler equations. Yeah, so probably well, it's natural to expect that there is in some sense, no, because evolution exists, but in which space, for example, and it can be so what is essentially what is X? So X does not have to be field, it may be probability distributions. It may be the flow in the space of probability distribution, and phi t may be the the rule how probability distribution evolves in time. And since I never use details of the flow or details of the space, it doesn't matter. So it's all construction should work.
And I have another more technical question. So when you consider transfer operator, or you call it Perron-Frobenius operator in Frisch model, so how quickly interaction decays? So how quickly decay conditional probability?
Well, they decay certainly, but not extremely quickly, I would say. They decay.
Oh, what is this?
It's different to say. Maybe parallel. Yeah, maybe. I have a picture, but well, there is a. They decay somewhat. So it does look to be exponential.
It does look.
doesn't look like exponential. No. And actually, it is reasonable because you see the intermittency in shell model is can be linked to the kind of very correlated events. So which are correlated from a moment that they start until they reach the dissipation rate. So the correlation is very long. And now when you consider the special structure function of special P, it linked to, if it looks like it is based on these events of certain lengths. Yeah, so in that sense, bigger the higher order structure function, longer the correlated events you need. So there is the correlation, actually correlation in shell model is rather strong, but it decays.
Because
so
you know, if it's very weak decay, then you can have the control of eigenvalues is much worse, and you can have effects like phase transitions and other things. So, I mean, it's
you're right. Yeah, you're right.
Alexei, your answer was ambiguous. So when you say power law, do you mean power law in wave number? That would still be
okay. Yeah. Good.
I mean,
So it's in a wave number. Yeah. It's probably exponential. Yeah, because it's power law in n. Yeah. Probably it's exponential.
Then there is no problem. Then yes.
Yeah. Probably. I'm just having this picture because it's in n, but n is already log.
Thank you.
Yeah.
Yeah. Thank you, Greg.
Next question by Luca.
Yeah, thank you. Well, indeed, the question is very similar to the one of Kostya. I mean, if you look at this figure, indeed, Alexei, I'm not so sure I agree with your conclusion. I mean, it seems that higher the moment is, and the more correlation you need to control in your conditional probability, right? But I mean, on the other hand, we might have a very intermittent distribution with fully uncorrelated multipliers. And the typical understanding that we have is when you have a very strong burst, they are also very rare and very fluctuate. I mean, the coherence in time is very short. Right? So I'm not, I mean, I understand your results as you show it here, but I'm not fully, I mean, because there is also another issue that you might not converge for high moments, not because you're not controlling all correlation, but simply because you have a bad approximation of your density, because after all, you calculated the density numerically, right?
I agree. Yeah, look, I agree fully. What I said is just I agree. So it's what I said. This interpretation I just said it's just speculations. No? Why it does not converge and why it will how it will converge better, I have no idea. The only thing that it converges rather well for the first two moments, and it doesn't converge for the high moment. It's converging, but very slowly. So this is all I can say. So.
But you didn't build in energy conservation here. Energy conservation would pin it at the third one.
Yeah, so, that probably will help. But how to do it?
Yeah, so if you pinned it at 3 to be 1, then that would make a big difference.
Yeah. If succeeding to pin to make it, probably it will improve the convergence a lot. Yeah. But how to? So far.
Next question, Alessandra Lanotte.
Yes, a very simple question. So you start from this table of compositions of symmetries, and then maybe I misunderstood, but it seems to me that you can use plus t or minus t in the same way. So, but not then. When you apply to a real system, which is either Euler equation or Navier-Stokes equation, then time direction matters. So what am I missing?
Well, time direction, essentially the time direction matters, but I never consider dynamics here, because what I consider is the whole study is about invariant measures. So the only property of the measure or probability measure I use is that it's invariant with respect to that flow. So I never use the fact that it's attractor, for example. And he is exactly here that time direction would matter. So I only use the fact that the measure is invariant. So, and I only prove that whenever you make a normalization, you also have a normalized measure for that new flow. So I don't really consider dynamics.
So just one comment. In a sense, maybe it's wrong what I'm saying, but in a sense, you're saying that if you consider an observable, even a Eulerian one, but which has the signature of time irreversibility, then this machine you could not apply.
No, let's say what is actually proved in a paper is that whenever I have a observable, whatever observable you have, and there is a certain ergodistic condition which is explicitly written how, then this observable with respect to the invariant measure will be the same as this observable average with respect to time. So just this, but time in a right direction. So direction of time is important because you see if you change direction, time direction, well, it's important. Time direction gives you the measure that you have. So because we consider, in some sense,
because you are considering already ergodic measure.
I will already consider the dynamics ended. So the end of the dynamics. I will consider already the measure which correspond to the final state of the dynamics. Only this. So in that sense, I just do not. This question of changing time direction just does not enter in the consideration. See.
Alexei, you said that generically you're going to get anomalous scaling. Do you see what there should be? There's a few examples where you have normal scaling, even though the system is nonlinear and has all the usual properties. Do you see what should happen for these different eigenvalues to be on a straight line?
Yeah. So there is even there. So is here. So the condition of the symmetry is the following. So it's one direction. So the hidden symmetry is weaker. In a sense, if the original symmetry has any scaling symmetry, so any combination of the temporal and spatial, so like Kolmogorov, then automatically you do have hidden symmetry. And automatically, all the you can directly see from this automatically has a straight line. But whenever you have a normalized symmetry satisfied, but all other symmetry are broken, typically you do not expect a straight line.
No.
You see, so the hidden symmetry is weaker in the sense that all the spatiotemporal symmetries in the original system, they imply the hidden symmetry, but not vice versa. So you can break all the symmetry in the original system, but still keep the other, the hidden one. And in this case, you don't expect a straight line. In the first case, it's directly the straight line. In the second case, it's not.
There's a question by Jeremy Beck.
Yes, hi, Alexei. I have a question regarding the fact that you didn't use space invariance. So which, and at the end, the hidden symmetry is telling you that this invariance is broken. So can you comment a bit on that?
Which invariance specifically?
So scale invariance, spatial scale invariance. So spatial scale invariance is not appearing in the commutation relation that you use. Yes, spatial scaling invariance, and basically at the end this invariance is broken by the anomalous scaling that you get.
Actually, it's slightly the way around because G is a spatial scaling. So the G is a spatial scaling which we want to keep. And what happens is that in the spatial scaling is broken by intermittency in the original system, but G star, which is induced symmetry in the normalized system, which is coming actually, which originates from spatial scaling.
So it's a kind of projection of the invariance.
Yes, it's kind of projection of spatial scaling invariance, and it's not broken. Okay. So you have self-similarity with respect to G star.
Okay, and then my second question regards the application to burgers, to possible application to burgers, for which have a very similar symmetry group, but then how do you interpret your conditional incompressibility in that case?
So you always ask good questions, no? So thank you. So essentially, it doesn't work for burgers because of what is so. Whenever you put Galilean transformation into this quotient construction, it does not generally work out. So you cannot essentially what is problematic is when you project to this representative set, you can project the flow, but the problem is that generally the projected measure is not invariant anymore, but you need it to be invariant. So it's only invariant if you have incompressibility condition. So it simply means that all this construction for Burgers sum just doesn't work. And you can see why.
Up here and understand.
Say it again, please. So essentially, this construction also algebraically separates incompressible system from compressible system. So in order to have this the normalized flow and normalized measure, you must have incompressibility. And whenever it's not incompressible, you still do have incompressible. You still do have normalized flow, but the measure which will be there has nothing to do with the original system. So you just you break the connection. So it's somehow solves this question.
What about things where incompressibility doesn't make sense, like general relativity, etc.?
You see, I have to look. What is important here is that it's not incompressibility in the fluid dynamical sense. It's just a name, because there is a condition, algebraic condition on essentially on a function which defines. So what is incompressibility means is that for every equivalence class you should define representative elements. So you should define what? You should define how to rescale time and how to choose the right, how to choose the reference frame for the full class. So incompressibility condition here is just a condition, special condition on this choice. So it's just a choice on this function A, and then there will be function B. And it's only for the fluid dynamics. For Navier-Stokes, it is incompressibility of the fluid. But for other systems, it's probably something different. The condition is there, it's written explicitly, but what it means physically for the different representations, it may be a different thing. No?
There's a comment by Greg.
Which I guess, which it wasn't addressed specifically in Alexei's talk.
You want to leave it written and not oral? That's fine.
Yeah, well, it was. I'm just saying it was addressed explicitly in Alexei's manuscript, but not so directly in his talk. So that's why I just brought it up, which is that Alexei's argument makes very close contact with the argument made by Uriel in his book and elsewhere, that the intermittency is associated with the space-time scaling symmetries of Euler indexed by the Holder exponent h. So there's a direct connection of Alexei's argument with that, which maybe he could even comment on himself.
Well, in some, yeah, thank you. Yeah, somehow, I would say so. Yeah. Hopefully, yeah, I hope so.
Well, I mean, I guess if you look at the I mean, there's a quite direct connection when you consider is sort of in your formalism, you know, the A and how it's, I mean, there's a direct relationship of if, that with the quantity H and Uriel's formulation.
Yes, somehow, yes. You see, somehow how you can see it is the following. You can take a measure, invariant measure, the measure which is invariant with a given H, right? So which has special temporal scaling with a given H. It will be also have this hidden symmetry automatically. But now take different measures with different H, and take a sum of them. So automatically, the sum of this measure is not symmetric with respect to any original symmetry because it's sum of measures with different H. But each of the measures is G-star symmetric. So the sum will be G-star symmetric. See, so this is directly how you see why intermittency is not in conflict with G-star symmetry, with this hidden symmetry, because whatever G-star does not this hidden symmetry does not depend on H at all. So whatever measure with given H you take, it is the same symmetry when you project. So it leads to the same symmetry after projecting. So you can cook up multifractal measure by considering measures from different H, but whenever you project, it's G-star symmetry.
Okay. There's no other question, so I think we can thank again both speakers. Thank you so much.